Hello everyone from my side. I guess this would be the first pizza lunch talk without pizza, which already makes for a big disappointment. So I will talk about a topic that's been understandably overshadowed by the corona outbreak. But it's something that I think it's still important that we discuss, that we keep track of, and that maybe also inform as many people about it as possible. So it kind of started a bit less than 1 year ago, when the Starlink company, owned by Elon Musk, launched the first batch of 60 satellites into low Earth orbit. So the Starlink, what they want to do is to build a big network of satellites around Earth in order to provide low latency and affordable internet around the globe. So far, they've launched about 360 satellites. They have approval to launch about 12,000 satellites, but their final plans are, the scope is supposed to be much bigger. And the numbers they're talking about is about 40,000, but those numbers are very unclear. So this is something that will definitely have a big impact on the human made satellites around Earth. So soon after the launch, many people around Earth saw this scene. This is a trail of very bright Starlink satellites crossing the sky. It was quite overwhelming. Actually, since then, there's been a significant rise in reports of UFO sightings. But it's also something that we should be concerned about if we care about dark skies. Because, before Starlink, all other satellites were actually quite dark. Typically, you don't really see them with your naked eye. And now suddenly you have these bright satellites crawling the space, which is concerning. Also to professional astronomers. So soon after the launch, images from observatories all around the world start to pop up on the internet. So this is an image showing bright Starlink traces on astronomy images. This one's taken from La Palma with a small telescope. And for example, this one with a bigger telescope on Chile. So astronomers were worried, and media thankfully picked up this. And since the first launch, there's been a constant stream of articles with very flashy titles asking whether SpaceX will threaten the astronomy. So what I want to talk today to you about is to present you all the ways in which Starlink and other companies could impact astronomy, and try to determine whether these satellites would actually be a threat or just a nuisance for us. Kind of a long story short, we don't really know what will be how bad these satellites will be for us. So I will present the problems with a fair share of Slavic pessimism and just go on the trying to present all the bad things that could happen. So I will mostly talk about optical astronomy, but then I will also touch upon other subjects. In a nutshell, the problem with optical astronomy is that the bright trails that are left by Starlink satellites, they completely saturate the detector, the CCD detector. And of course, all the information under the trail is lost. But what's even more concerning is that because the way the CCDs are built and the way we read the data the signals from the CCDs, then such saturated trails can create ghost images and residual images on the other parts of the image. And so if you're interested in doing some very high precision photometry, then well, you cannot really trust an image like that, and well, you may as well just throw it away. And so that's why this problem is so severe. To put the things into perspective, this is the picture before Starlink started launching satellites. So there were about 20,000 man-made objects in low Earth orbit. Most of that were actually pieces of debris. There's about 5,000 satellites in orbit, and a few thousand of those are actually operational. And if you look at the sky at any point during the night, then there will be about 600 to 700 of those objects on the sky at that time. But they are very faint, so you don't really see them. And now many companies have announced that they want to build their networks around Earth. Starlink is by far the most ambitious, given the number of satellites. And so we're going from a few thousand satellites to 30 to 50,000 in, if we believe the predictions, in a matter of few years, which is quite crazy. So this means that, well, at any point during the night, you will have, well, 1,000 or even more satellites on the sky. But the problem now is that, especially at the beginning or at the end of the night, those satellites will be extremely bright and brighter than practically all the other objects that are now in space. So that's quite concerning. Saying that, last week there was a news telling that one web company who already launched about 80 satellites went insolvent, so they cannot get investors anymore, partly because of coronavirus, but mostly because they're just not competitive with Starlink. So we'll see what will happen with the satellites that are already in orbit, but at least it seems like there's this is if I can be a bit mean, this is one less problem to worry about. You probably know that these satellites don't really have their own sources of light, or, well, even if they do have some light, this is very faint. But why we see them so bright is because the light from the sun reflects from the satellites, and we see them while we are already in Earth's shadow. So in order to assess what's the impact of these satellites for us, for astronomy, we would ideally like to know what will be the number of satellites at each point during the night in the sky, how bright they will be, and how this depends on where on Earth we actually observe them. We cannot really do this very precisely because we just don't know the details. We don't know the actual number of satellites that will be launched. We don't know orbital parameters. We don't know satellite reflectivity, etc. But you can make some smart assumptions and then just look at the general trends. And that's what several people already did. This is what I found so far concerning the literature. I guess the second reference is goes the most into detail. This is a paper that's been accepted to ANA, and I will show some results soon. So basically, the larger your field of view, the larger the field of view of telescope in the camera, the greater the chance that a satellite will cross your field of view while you're making an exposure. So surveys with large fields of view will be the most impacted by the satellites. And this means that especially transient science will be, well, the surveys that are searching for transients those surveys will have the most problems. There's been a lot of surveys built in recent years for transients. It's quite a hot topic, partly due to gravitational wave counterparts, but also there's this project, Vera Rubin Observatory, formerly known as LSST. This will be, it is being built in Chile, and it will become operational in a few years. It's a very special telescope with kind of unprecedented characteristics. It has a very large mirror of 8 meters diameter, and it also has very big field of view, almost 10 square degrees. So with this kind of characteristics, it will find a lot of transients, 10,000 per night, like 1,000 supernovae per night. So it will really be a transient machine. But these characteristics also make it very vulnerable to all the surveys, to the satellites. So the impact that has been calculated by that paper that I just mentioned is summarized in this table. So the models by these guys have been computed for ESO instruments specifically, plus they added LSST, and they look into the for each camera, which has a certain field of view, and they assume that you make an exposure of a certain time, and then they calculate what will be the contaminated fraction of the observable sky during the night. This can be also interpreted as what is the probability that your exposure will be disturbed by at least one of the satellites. As you know, we already start doing some observations or calibrations during the twilight. And then astronomical night is reserved for the most sensitive observations. Yeah, LSST is expected will be the most impacted here. The satellites can disturb the observations quite long into the night. The other instruments are on VLT are not expected to be disturbed a lot, though I was a bit surprised that multi-object spectroscopy could actually have a bit of problem. So these numbers can be, so this has been calculated assuming that Starlink has approved 12,000 satellites, and these numbers have to be scaled appropriately if there will actually be 40,000 of Starlink satellites on the sky. You can also scale these numbers if you play with exposure time or field of view. So for LSST, what will be especially problematic will be twilight observations of asteroids, and yeah, of course, high precision cosmology. So an assessment is that if there's nothing done concerning the brightness of the satellites, then I think that operational time of LSST to do the tasks that they set out to do is about 10 years. And if the satellites stay as bright as they are, then this will have to be, you will have to add another 4 years of observation time just to reach your goals. So you may know that Elon Musk can be quite arrogant with his statements, and a while ago he said that astronomy will have zero impact, that satellites will have zero impact on astronomy, which of course is just ridiculous. There's been several solutions proposed. First, Starlink proposed that they could make satellites less reflective. So they already launched one satellite into orbit that's been coated with something that's, well, less reflective. And very recently, the first measurements have been reported. For now, only in G magnitude, and they measure that this darkened satellite is for less than 1 magnitude fainter than the other satellites, which well, this is quite okay in terms of that this reduces the number of satellites that will be visible by naked eye. But for something like LSST, it still doesn't help, so they will have to do much better. Then the other obvious solution is scheduling. So if you know where the satellites are during the night, then you can schedule your observation in such a way that you don't get contamination by satellites. This doesn't really work very well if you have 50,000 satellites in orbit. And also, this automatically means that your observations will be less efficient, so you lose some time. But it also assumes that you have a full cooperation of all the companies with satellites. And well, this is a slightly ridiculous slide because I would never even think to put it there. But so very early, when astronomers raised concern, Elon Musk said, well, but ground astronomy is passé anyway because there's atmosphere, which is problematic. We should just put all the telescopes into space anyway. And this is a slide that I made for another talk, public talk, so I don't even want to go into detail because I don't think I need to convince you that, well, space astronomy is not a replacement of ground astronomy and that we really need ground astronomy. So much about optical. Now, I will shortly say a few words about radio astronomy. So I'm not really an expert in radio astronomy, so you can later ask radio astronomers in the room for gory details, but the fact is that, of course, optical astronomers now are quite enraged by this contamination, but radio astronomers had to deal with this from the beginning of radio astronomy. And very early on, they realized that, well, if we don't do something, then we just cannot do radio astronomy. So I think in the late 50s, they managed to allocate some of the frequencies in the first frequencies in the radio spectrum to be protected only for astronomy use. Just to show you how crazy the radio spectrum actually is. So this is the radio spectrum, and it shows the frequency allocations across the spectrum. I don't know if you can actually see my mouse on the screen, but the very, very bright yellow color, these are the astronomy bands that are protected for astronomy. So you can see they are here and there, you can see them. But what's really crazy about this spectrum is you can see that how crowded it is. And also, regulation doesn't actually mean that you will have no interference in your protected bands. As well, that's basically what Liam said just before. So here's a nice example from the Iridium satellite. Iridium satellites are well-known telecommunication satellites. And it turns out that they actually contaminate. So this is here. You can see the band that is in principle astronomy band, but there's an interference coming from the signal of this satellites, and this problem has been known for decades, and it's still the satellites are still radio loud in these protected frequencies. So this kind of illustrates and the problem that even though, of course, you have protected bands, that doesn't really necessarily mean that there will be no interference from all kinds of satellites, radars, ground transmitters, etc. And so we don't really know at this point whether Starlink and other companies will be problematic in this sense. But if they are, it will be a big problem. So as I said, I'm not really a radio astronomer, so I was quite surprised with all this crowded spectrum. And also, here's a nice worrisome quote from the person who's kind of responsible for the protecting of the astronomy spectrum, and he's also quite worried about how crowded the spectrum is and how more and more of this contaminated signals are coming into the astronomy bands. Okay, a quick jump to the space. So we have astronomy satellites, well, satellites that are made for astronomy research. We have them in low Earth orbit. This is a very short list, very biased. So there's a lot of satellites that are in orbit are dedicated to transient research, which I'm very interested in. So I know of those satellites. In very near future, there will be satellites launched into low Earth orbit, and there's also big missions that are planned. Well, in the state of proposal, but still they're planned to be there in the 30s. So we are also interested in, astronomers are interested in this, in the low Earth orbit. Now, the problem is that even though the space around Earth is very big, when you have so many human-made objects flying around, at some point they will meet each other and they can even collide. So ground operators in recent years have to adapt some of the orbits more and more in order to prevent collisions. So this is a famous example from 2012 when Fermi almost collided with a Russian satellite. And in 2009, there was actually a collision between an Iridium satellite and one of the Russian satellites that caused a lot of debris. And yeah, we don't really have, so we as a humanity, we don't have a solution for the problem of the debris in low Earth orbit. Not so much because of lack of technology, but mostly because it's really difficult to find international agreements. And the problem of the debris is quite serious because each collision can cause a lot of extra debris, and there's something called the Kessler Syndrome, which means that you could actually get a cascade collision of debris. So two satellites cause debris, and those debris then collide with other satellites, and in the end you get a huge cloud of debris in low Earth orbit that could eventually cut off humanity from space for quite a while. So it's quite a serious concern. And in this light, it's worrisome that all these new satellites of private companies are allowed to be launched into space without having a real solution for the debris. And on a side note, there was already in September last year, or maybe October, there was a near, let's say, near encounter event between one of the Starlink satellites and one of the ESA's research satellites. And there was a very bad communication between Starlink and ESA, and let's just hope that this is not a standard. So I will very shortly just mention a few things about more wide, public-wise impact. This is a nice map from a recent map showing the light pollution on Earth. Turns out most of the people in Europe and US live in a light polluted area, meaning that we can only see the brightest stars in the sky. And in a way, satellites, if they keep being as bright as they are, then they kind of add to this pollution. And unlike the city lights where you can kind of escape from and going to some dark place on Earth, you cannot really escape the satellites. So it's a bit depressing when you think about it. Saying that, satellites, at least these Starlink satellites, most of them will be, well, they will be especially visible during dusk and dawn. And otherwise, during the night, most of them will be darker than what we can see with naked eye. So at least that's somehow reassuring. There have been many actions taken. I don't know what was the effect of that, except to notify the public that this is a problem. Fortunately, the media picked up the story, so there's been a lot of talk about the problem, and we hope that, well, I hope that we keep the momentum of this, even though we are, of course, now affected by a different and much more pressing problem. So with this, I would conclude my talk. I think that unless this corona outbreak is much worse than we think it is, then mega constellations will happen in the next few years. So I don't know exactly what will be the impact of those constellations, but there will be some impact, and we'll have to get used to that and adapt to some extent. And yeah, we have to keep track of it and inform the public that this is a problem, and hopefully this telecommunication satellite network, which we need, of course, can coexist with astronomers. So thank you.